All right, so we've talked about ionic and covalent bonding. We haven't talked yet about what holds metals together. So if you have a metal knife or, a horseshoe or whatever, any chunk of metal, what's holding those atoms together? Because they're not ionic because, a metal can't really give an electron to another metal, and they also can't share. So there's going to be something different going on. So metal atoms have what are called mobile or delocalized electrons. And this creates what's called a sea of electrons. And that sea of electrons, of course, is negative. So the positive metal nuclei are going to be attracted to and held in place within that sea of electrons. So to visualize this, pardon me, you can think of metal atoms as having a loose hold on their valence electrons. They have very low ionization energies, and so the electrons are not held to them very tightly. So if you imagine any of these little yellow electrons, maybe you could say it originally belonged to, this guy right here in the lower right, but as it is moving around, it may end up, sort of zipping around this guy for a little while, and then going around this guy, and it's just kind of moving all throughout this entire matrix of atoms. All right. So then the question becomes, all right, if the electrons are free to move around, how does that hold the atoms together? Well, when you have all these negative electrons, all these negative particles that are just kind of like able to go wherever they want to in this entire area among all of these atoms, that creates what's called, again, a sea of electrons, this field of negative charge. And then the positive nuclei of our, let's say these are copper atoms, would be held in place because they're all attracted to that negative sea of electrons. And so that's the sea of electrons model for metals, and it leads to a couple different properties. One of those is the fact that metals tend to be conductive of electricity. And the reason for that, and I may have these out of order, but it's all, we're going to talk about all of these. The reason that metals conduct electricity so well is because if you imagine like a positive lead from a battery and a negative lead from a battery, if these little red guys represent the atoms and these little blue guys are the electrons that are free to move around, electricity can be conducted because the electrons are in motion, they're already mobile. And so they're going to be attracted to, the positive side, and then more electrons can be, drawn into the metal. As it loses electrons to the left, it's going to replace those electrons to the right from the battery, and that flow of electrons is conducting electricity. Metals are also malleable, so if you hit them with a hammer, they rearrange, and they rearrange without actually breaking apart usually, unless you hit it with a lot of force, or if you have a really disjointed, disorganized metallic crystal. Because what happens is the sea of electrons is the same throughout. So, in an ionic compound, you have positive, negative alternating. And so we talked about this with ionic properties, when ionic crystals get misaligned and you have positive lined up with positive, then they don't stay that way. They repel each other and they shatter. So that's what makes ionic crystals brittle, right? And so with a metallic crystal, though, the negative sea of electrons is just the same throughout. So rearranging the nuclei of these metallic atoms within that sea of electrons doesn't give it any reason for those atoms to then repel each other. It just sort of stays rearranged. And that's what a malleable metal is. It's just rearranged atoms. But as long as they're not repelling each other, it's not going to shatter. And the last property of metals that's unique is a fairly high melting point. And the biggest reason for this is because this sea of electrons is pretty attractive for the atoms, and also because the arrangement of the metal atoms within a crystal is pretty dense, pretty tight. The atoms are able to get close to each other, which allows for their attraction to become even greater. And so it takes a high temperature for most metals to melt. Of course, we have exceptions like mercury, which is a liquid at room temperature. But for most metals, the melting point is going to be pretty significant, in the hundreds, and in many cases, thousands of degrees Celsius. Okay, and then our last topic of our unit is to distinguish between the properties of ionic, covalent, and metallic compounds, so distinguishing between them by their properties. And then, of course, why those properties exist. And we're going to do a lab with this, so it's important that you understand what these properties are and why they exist. Okay, so let's talk about melting point. Ionic compounds, we've already talked about this, have a very high melting point. All right, and that does technically depend on lattice energy, but even if lattice energy is relatively low, like in table salt, those ions attract each other enough that it takes over 1,000 degrees Celsius to melt these things. So all ionic compounds are solids at room temperature, and most of them are upwards of 1,000 or 2,000 Celsius to melt them. So very, very difficult. Covalent compounds are usually low. In fact, a lot of covalent compounds are gases or liquids at room temperature. Now there are some with really high melting points, and that just depends on the structure with which they are held together. So, for example, a diamond is technically a covalent compound, but because its unique arrangement of atoms and in the unique kind of bonding that it has an extremely high melting point. But for the most part, most covalent compounds can be identified by their low melting point. So in the lab, if you have a white solid and you want to know whether it's ionic or covalent, one way would be to test its melting point. If you're able to easily melt it using the Bunsen burners in the lab, it's probably going to be covalent. Metallic, generally high, although again, you have things like mercury that have very low melting point. Also gallium. There's a few other metals that don't take, lead doesn't take a super high temperature to melt, but for the most part, these are pretty high. You can also test conductivity. Ionic compounds, we looked at this with the light bulb. If you dissolve them or melt them, and it allows those positive and negative ions to be mobile and to move around, you can get them to conduct electricity, but not, of course, in the solid form, because then the positive and negative ions can't move anywhere, and so they can't conduct current. Covalent compounds, though, even if you dissolve them or melt them, are not going to conduct electricity, and that's because the particles, the individual particles themselves, while they may be polar, they are not entirely positive or negative. They just maybe have a positive end and a negative end, but they do not conduct electricity because the entire particle is neutral. And then metals are very conductive. So even as a solid, of course, you can conduct electricity through a metal for the reasons that we just talked about. All right, you can also test solubility in water. How well does something dissolve in water? If it's an ionic compound, generally they are soluble in water, although there are plenty of ionic compounds that you'll have a hard time that you'll have a hard time dissolving. And that is, generally speaking, because they have very high lattice energies. So something with, aluminum nitride, which is +3 and -3, has a high enough lattice energy that its melting point is going to be super high, okay? But generally, most ionic compounds, you could say, have at least some amount of ability to dissolve in water. And we'll talk in more detail about that process when we get into our solutions unit second semester. Covalent compounds, like, for example, sugar, are generally pretty soluble in water, but if they're non-polar, like, let's say, wax, which is paraffin, that's non-polar, it's not going to dissolve in water, because again, like dissolves like, so water is polar, it will only typically dissolve other polar covalent compounds. And then metals, of course, don't dissolve in water because they're just held together too tightly within their metallic bonds. Malleability, we have ionic compounds. We already talked about this. Ionic compounds are brittle because if you get those positive and negative ions lined up, they're going to repel. Covalent compounds, usually brittle if they're solid, of course. If you think about ice as an example, that's a covalent compound. And you hit it with a hammer, it doesn't take a new shape. It shatters, and that's again because of the very strong hydrogen bonds that, if rearranged, almost like ions in a salt crystal, if rearranged, they will repel each other. But again, that's only in the solid state, right? And then metallic, we just talked about, are very malleable, and that's because they can be rearranged within their sea of electrons and not repel each other. So our next step is going to be to actually do a lab where you're looking at ionic versus covalent compounds, which you may not be able to tell what they are just by looking at them, because they'll be solids and they're all, typically white solids. So you'll have to put them through a couple of these tests, and then looking at the results of those tests, you'll be able to figure out whether it's ionic or covalent.